Hi everyone. In this lesson I'd like to talk about the discriminant just a little bit more. You remember in the quadratic formula that we solved to find the solution of a quadratic equation, x is negative b plus or minus the square root of b squared minus 4ac all over 2a. And this expression under the radical we call the discriminant because it discriminates between the types of solutions that you may obtain. If the discriminant is a perfect square, then when you take the square root of a perfect square, the radical is going to go away. And that means that there won't be any square roots, and you're just going to end up with two rational solutions. And if you ever get two rational solutions, that also means that the original quadratic equation could have been solved by factoring. Okay? Now, if the discriminant is a positive number, but it's not a perfect square, then you're not going to be able to get rid of the square root, and you're going to end up with two irrational solutions. Now, you'll remember that a rational number is a number that either terminates or repeats, and an irrational number is a number that neither terminates nor repeats. And so when you do those on your calculator, you get a whole bunch of decimals. All right, and if you get a bunch of decimals, or if you can't get rid of the square root, that means that the original quadratic equation could not have been solved by factoring. So back in your beginning algebra class, when you were wandering, sometimes you'd be asked to factor a trinomial, and you look in the back of the book and it said it was prime after maybe banging your head on the desk a little bit because you weren't able to factor it, and you wish there was some way to know when a trinomial was factorable. Well, this is actually the answer to that question. If the discriminant, if your b squared minus 4ac is a perfect square, then it's going to be factorable, and if it's not a perfect square, then it's not going to be factorable. Okay. Notice also that if the discriminant is equal to 0 exactly, then this whole term will just disappear, and you'll get negative b over 2a, which is exactly one rational solution, at least assuming that a and b are rational numbers. And then if the discriminant is a negative number, then you'd have the square root of a negative number. That gives you an expression with i's in it, and that will result in two non-real solutions. Okay? Now we can use our quadratic program, if we have that programmed into our graphing calculator, to accomplish something pretty much the same thing a little more easily. So suppose I was given this quadratic equation. I could very quickly put that into my graphing calculator here, run my quad program. A would be 6, C would be negative 19, and C would be negative 20. And I see that I get nice rational numbers, and so since these are rational numbers, nice numbers without a bunch of nasty decimals in it, that is going to be two rational solutions that would tell me that the discriminant was a perfect square, but more importantly it would tell me that this is factorable. All right, so my solutions were t equals 4 and t equals negative 5, 6. And not only does that tell me it's factorable, but it also gives me an idea how to factor it, because I can take these solutions and work backwards. If I bring the 4 on this side and I multiply both sides of this equation by 6 and then bring the 5 over, then these two binomials are going to end up being the factors of this trinomial. Let's try it and see. If I were to take t minus 4 and multiply that by the 6t plus 5, does that work? I'd get 6t squared. Well, that works there. And then let me write that a little more clearly. and then the outers would give you 5t, and the inners are minus 24t. So 5 minus 24, sure enough, that's negative 19t, and then the negative 4 times 5 is the negative 20. And so if you use your quadratic formula, whether by hand or if you have it programmed in your calculator, if you can get your solutions, and those solutions are nice rational numbers, then that tells you that this could be factored, and it even helps you to factor it. Okay? Now, let's do one more example like this. This is x squared plus 5x equals 9. I'd, of course, want to write that in standard form first. So bring the 9 over so you can identify your a, b, and c. Let's plug this one in. My a is 1. My b is 5. My c is negative 9. And in this case, I get some really nasty decimal answers. That's not a rational number. That's going to represent an irrational number. It's a non-terminating, non-repeating decimal. And so in this case, I can see from the quad program that there at least appears that there's 2 irrational solutions. And so that would tell me that the discriminant is not a perfect square, but more importantly, for where we might want to use the idea of the discriminant, is this isn't going to be factorable. I'm not going to be able to find any factors of 9 that's going to combine to give me 5. Now this is a fairly easy one. You could probably recognize that right off the bat, but it does illustrate the principle that when you use the quadratic formula and you get values, numbers, solutions to it that aren't rational numbers, then you're not going to be able to factor that, at least not by the techniques of factoring that you learned in beginning algebra. Okay?